Hello and welcome to Permutations, the next step of our counting and probability. So we're going to arrange the letters CAT, C-A-T in all possible orders, making some nonsensical words along the way. How many possibilities are there? Well, we can do this by a method that we sometimes call brute force, which is not using a mathematical method, but just listing all the possibilities out. So I could say all the ones that start with C, which would be C-A-T and C-T-A. Then I can do all the ones that start with A, which is A-C-T, and A-T-C. And then I can do all the ones that start with T, as in T-A-C or T-C-A. Heck, if we add a G in there, we have DNA. Ooh, but there are 6 of them. So 6 possibilities with 3 letters. Let's try to arrange the letters BJPS in all possible orders. This is actually going to take a little bit of time, because if you think about it, for B, if I start with B, then I have 3 letters that follow. Well, instead of actually listing out all the possible ways I can take J, P, and S and switch them around, I already know that given any 3 letters, it's going to be 6 possibilities. So really, instead of arranging all of these in order, let's just kind of answer the how many possibilities are there. With JPS, I know that there are 6. So there's 6 of them starting with B. Then there would also be 6 of them starting with J. Then there would be 6 of them starting with P. And then there'd be 6 of them starting with S. And if I add all those up, there are 24. In other words, there were 6 times another 4 equal to 24. So returning back up to the CAT one, if we kind of look at it from the perspective of I have the ones that start with a C, and there were 2 of those. The ones that start with an A, and there were 2 of those. And the ones that start with a T, there were 2 of those. It's kind of like this was just 3 times 2. 3 sets of 2 different possibilities. And this was, if I can replace this around, 4 times 3 times 2. And if you add another letter to BJPS, you might have 5 times 4 times 3 times 2. This actually occurs so commonly that we created an operation called the factorial. Factorial is kind of fun. You could say this says find the number 4. But what we say is 4 factorial. Or when I got to college, I had a roommate that called it 4 bang. Must be a West Coast thing. But this means 4 times 3 times 2 times 1. In fact, for the factorial, I can give a general definition of n factorial is the same thing as n times n minus 1 times n minus 2 all the way down to 1. 5 factorial, let's finish what 4 factorial is. 4 times 3 times 2 times 1 is 24. We know that from up above. 5 factorial is 5 times 4 times 3 times 2 times 1, which is really the same as 5 times 4 factorial, which we knew was 5 times 24. And 5 times 24 is 5 times 4 plus 100, or 120. So we can use previous factorials to get other ones, or you could just multiply out 5 times 4 times 3 times 2 times 1. 0 factorial is one of those that's just defined. We're going to create a definition for what 0 factorial is. In fact, we can kind of find out, and this is a good time to bring up your calculator. If you go to the menu and you look under probability, you're going to see the factorial is the first possibility. And if you type your number first, I'll type 0 and look up what it thinks 0 factorial is, it's going to give me 1. And you're like, well, what is 1 factorial? You can probably guess that 1 factorial is also 1. So just by definition, because it makes a lot of other parts of what we're going to be doing turn out nicely, 0 factorial is equal to 1, and you're just going to need to know that. 100 factorial, I'm not going to write this all out. This one I'm going to go ahead and use a calculator. If I go to the calculator and try to plug in 100 factorial, it's going to, wow, this one gives it. Okay, I'm going to pause this and show you something even neater. Meet the TI-84, a calculator many of you will not need to use. But if I go and find this in the probability menu of this one, and I hit 100 factorial, it will freak out on me. It overflows. It's too many digits for it to handle. Not for yours. Apparently, we can just keep scrolling and look at all these digits. And there are a lot of digits. Lots of them. That is a huge, huge number. My point is, this is actually too big to write, and we don't really want to approximate it. So there's a limit to how big your calculator can get with this. In fact, just for curiosity, go ahead and try 1000 factorial. I'll be amazed if your calculator can show this one, because this is going to be correct. Okay, yes, mine just says 1000 factorial. Let me try hitting the control approximate. Okay, it says infinity. It's too big for it. Overflow replaced by. There we go. So it did give me an error. Too big to write really is that. If I do, let's try 7 factorial over 4 factorial. We're going to start seeing some of these happen. So this is kind of neat. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. And watch how these both just drop out. And so really it's 7 times 6 times 5, or 42 times 5, or 210. And if I have 9 factorial over 4 factorial, 5 factorial, that is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. I always like lining them up vertically if there's just as many. And then just start playing a little slash game. And let's see how far we can slash down some of this stuff. So 4 times 2 is 8, and 3 goes into 9 3 times, or 6 twice. And you end up with just 21 times 6, or 186. So a permutation. This is kind of what this math is leading into. And a permutation is defined as an arrangement of elements in a set in a definite order. To an extent, when you walk into the classroom, every possible way that each of you could sit in the class, every possible way you could have a seating chart, is in a sense a permutation. Maybe you're sitting by the window, maybe you're sitting by the door, maybe you're sitting by the door and everyone else has changed around. All the different ways that can happen is a permutation. And in probability, it's important to understand how all the different possibilities can affect the likelihood that something will happen. If you cannot reuse an element, and in the analogy we just did of the seating chart, if you cannot reuse an element means if you can occupy 2 seats at the same time. But if you cannot reuse an element, then the number of permutations of n elements is n factorial. This is kind of a neat thing. If there's 26 seats in a classroom, and I know, well, let's just go with our example. If there's 9 seats in a classroom and there are 9 kids, then the number of different ways that you can have people sit is 9 factorial. That's a lot of possibilities. That's an incredible number of possibilities just for 9 kids in one class. You can imagine how big 26, well, it's the biggest math class we have with 25 kids maybe. If I go 25 factorial, and you figure out how many possible ways they can sit in the classroom, wow. I mean, you have to, okay, I can't even launch into how absolutely unbelievably big that number is. And that's just 25 kids, one class, and all the different ways that they can be seated. So, if we take kind of a common word like Voyager, yes, I'm a Star Trek fan, so I'm going to pick that one, and talk about the number of different words or nonsensical words. And I like that word, nonsensical. Just means doesn't make sense. How many nonsensical words we can make with this thing using all the letters. Well, there are 7 letters. I can just say 7 factorial. And 7 factorial is equal to, if I plug it into a calculator, 5040. You can do it by hand, but I'm not going to make you. For the most part, you're going to be allowed to use a calculator in this. Just show the factorial and then plug and chug, and you'll see the 5040. But using only 5 letters is a little bit of a different case. because basically, instead of saying 7 times 6 times 5 times 4 times 3 times 2 times 1, what I want to do is I want to say not this, but just 5 of them. So 7 for the first spot, and once I've used 7, then I have 6 for the next spot, and 5 for the next spot, then 4, then 3 possibilities remaining, but I'm not using the rest of them. This is the same thing as saying 7 factorial divided by 5 factorial, which is also the same thing as saying 7 factorial divided by, not divided by 5 factorial, divided by 2 factorial. And this is the same thing as saying 7 factorial divided by 7 minus 5 factorial. Why is that important? Well, this 7 is the number of letters we have, and this 5 is the number of letters we are using, which actually kind of makes this 2 the number of letters left out. Partially why they're divided out. Now, I know you're like, well, what is this? This actually is a much more simply expressed as 7 pick 5. And if I go to the calculator, I can actually, oops, I'm picking the wrong one. I can say, what is 7 factorial divided by 2 factorial? It's one way I could type it in. Forgive the delay here, but hopefully you're doing this on your own too. Or I can say, what is 7? And then go to the menu, to the probability, permutations. Oops, typing this wrong. I want to hit, forgot that it does it this way. I actually want to hit that and then say 7, comma, 2, 5 for 7 pick 5, and it'll give me the same thing. This is the calculator's way of typing in 7 pick 5, but this is the way we write it out by hand. And I'm less concerned with the number and more concerned that you have the idea down, but we'll write the number. This is 2,520. And the symbol NPR, not the National Public Radio, but the symbol NPR is used to indicate the number of elements, the number of permutations of n elements taken r at a time. If you're having trouble with these variable definitions, just replace n and r with actual numbers. Like, for instance, 7 pick 5 is used to indicate the number of permutations of 7 elements taken 5 at a time. And if we can get a very easy sort of way to write this out, for instance, this looks like a complicated word problem, but when I see Mario, Sandy, Fred, and Shanna are running for the offices of President, Secretary, and Treasurer, what I see are really 4 people, and I see 1, 2, 3 positions. And I'm going to say 3 different positions. That's kind of important for what's going to follow. These are 3 different positions. And since they're, sorry, it's hard to talk and write at the same time when I do these. And since they're 3 different positions, in how many ways can these offices be filled? Basically, I want 4 people, and I'm going to pick 3 of them. Little side note here. I like saying for permutation, I like using the word pick because they start with the same letter. Later on, for combination, I'm going to have the word choose because they also start with the same letter. So you're going to see me do that quite a bit. Now, from the definition of permutation, a permutation, 4 to pick 3, means 4 factorial over 4 minus 3 factorial. And if it's 4 factorial over 4 minus 3 factorial, you could type that in the calculator if you really want to, but really this should not be hard. That is the same thing as 4 times 3 times 2 times 1 over, and 4 minus 3 factorial just means 1. So that's just 4 times 3 times 2, which is 24. Now, I kind of learned this, and I remember learning this. I actually learned this in 7th grade. Looked back at my math binders and saw that. And one of the things that my teacher told me back then, too, is that this tells me the number I start at, and this tells me how many places I go. So the 4 was kind of the start, and then we go 3 places. And that's what 4 pick 3 meant. this is the definition. What I want from you guys is to see either one of these or these, and I'm pretty sure I'll let Mrs. Manton kind of decide. I'm pretty sure she wants to see this for several of you guys too. So and that helps you understand what the definition of this thing is. Okay, moving on down. If gold, silver, and bronze medals are to be awarded to the first of 3 finishers in an 8-person race, how many ways can the medals be awarded? 8-person. So I have 8 people I can pick from. And notice how we have gold, silver, and bronze. These are actually, I'm going to write the word different here again because it matters. Maybe the same 3 people finished in the top 3, but they got different medals. So there's different permutations. Remember, possibility is kind of synonymous here to permutation. And permutation is one of the ways that these things can happen, that the set can be arranged. So I'm going to pick 3, and I'm going to show sort of both ways here. So the definition way to write this out is 8 factorial over 8 minus 3 factorial. The sort of factorial way to write this out is to go 3 places, 8 times 7 times 6. And the calculator way to enter and check is either just type in 8 times 7 times 6, which is probably the easiest at this point, or to go go back to the factorial menu, probability, not factorial, my bad. Let me pause this. There we go. Probability of, 8 pick 3. I get the same thing, 336. So then number 12, we get how many ways can 7 different objects be arranged in a line on a shelf. If there's 7 different objects arranged, then and they're in a line, I kind of like putting here order matters, meaning each spot is different from the other one. So if they're arranged in a line on a shelf, that's just going to be 7 factorial. And 7 factorial, I believe we already did, was the same as the Voyager example. That is 5040. If we arrange the words Tuesday, Tuesday has 7 letters, 7 different letters, which is important. And I'm going to pick 4 of them. So you're starting to get the idea that this is not terribly difficult. That is 7 factorial over 7 minus 4 factorial, or 7 times 6 times 5 times 4. And if I go calculator way to enter it, again, menu, probability, permutation, 7, comma, 4 is the easiest way to do it. 840. So what if they're repeated letters? Remember, we kind of said they're all different. Well, sometimes they might not be different. Like in the word Katrina, I have 2 A's. I'm going to start with the number of letters in Katrina. There are 7 letters. And if they were all different, then it would be 7 factorial. Now, because the A's are similar, I actually have to, and I kind of think of this way, I have to divide out the repeats. So what I'm going to do is I'm going to take 7 factorial, and this is for the 7 letters, and then I'm going to look at how many A's there are. There are 2 A's, and that means that every time those A's could have swapped places, that's actually the same possibility. And the A's can swap places 2 factorial times. So we basically cut all the possibilities in half. And instead of 5040, we're going to end up with 2520 possibilities. If I look at the word parallel, we now have multiple repeats. That is now 8 letters, 8 factorial. But I have 2 A's and I have 3 L's. And that's going to be 2 factorial over 3 factorial. 2 factorial, 3 factorial in the denominator. Now, you could write this all out. I kind of recommend, let's just go calculator to be sure we get this right. 8 factorial over 2 factorial, 3 factorial. Right now it's actually easier to type that out like this, 3360. 3 apples, 2 oranges, 4 pears, and 1 banana given to 10 children. Let's actually count the number of pieces of fruit we have. That is 5 pieces of fruit. Good, no one's left out. 10 pieces of fruit. No one's left out. 10 fruit pieces. I have 10 children, so really that just should be 10 factorial, but some of the fruit's the same. And when it's the same, we're going to divide out the commonalities. 3 apples, so 3 factorial. 2 oranges, 2 factorial. 4 pears, 4 factorial. Really don't need to put 1 factorial. And again, going back to a calculator, that's going to be 10 factorial. So I'm going to build a fraction, 10 factorial over, and it was 2 factorial, 3 factorial, 4 factorial. So 2 factorial, 3 factorial, and 4 factorial. It's kind of quicker to write that like that. 12,600. Different ways that could happen. Lastly, these are some fun words I found online in period 7. This is why I was giggling while you guys were taking your test. This is an actual word. You could try to say it. Okay, flibbertigibbet. Okay, that's someone who is flighty, careless, and frivolous, and who talks a lot. To me, this describes many of my wonderful period 7 kids. This is my shout out to you guys. We got to count the number of letters in here. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 letters. 15 factorial. And then we look to see which ones are in common. So you just kind of have to be careful. F's, I have 1. L's, I have 1. I's, we have 3. B's, we have 1, 2, 3, 4. E's, we have 2. R's, 1. T's, 1, 2. I's, we already did. G's are 1. B's, we already did. E and T, and that's it. So these are our repeats. 3 factorial, 4 factorial, 2 factorial, 2 factorial. Punch that in. I'll pause it while I do. This is the number I came up with. 227026800. I think I'm actually missing a 0. Yep. One more 0. And that would be 2,270,268,000 possible ways. Effervescence, another word. Fizz, I know that word. Well, we can take this and break it up into 3. This is kind of how I count sometimes. So I count 13 letters, 13 factorial. Then let's check the number of E's. We actually have more E's here. 1, 2, 3, 4, 5 E's, if I counted right. F's, we have 2. R's, 1. V's, 1. S's, 1. But C's, we have 2. And so this is going to be 13 factorial over 5 factorial, 2 factorial, 2 factorial. And that will be equal to, dramatic pause, 12,972,960 possibilities. That's it.